So here's another improper integral that I think certainly stands out because you can clearly see that infinity as your upper limit of integration. And those are just nicer to have because they're more obvious. You know there's a problem. The very first thing to do is address that problem before you start thinking about anything about the antiderivative. This is absolutely your first step. That's what's going to give you a good amount of points on the Unit 3 test. Then you can come out here and say, okay, here's my integral. It was the integral of x squared e to the negative x dx. So once you've addressed the problem, now you're sort of moving on to, now let's consider, like, how do I evaluate that integral? And let me put the limits of integration in from 0 to b. And you're really starting to think, okay, is it a basic integral? Definitely not. Is it u substitution? That's not going to work here either because you've got a polynomial up against an exponential. And there's no good u substitution that's going to make this work with the way that this has set up itself. So what I need to do is remind myself that there is a fancy method of integration, integration by parts. And that's what I'm going to have to use on this particular problem. And if you really kind of look at that inside piece there, if I really look at what this is one of those guys that was a good form to use that tabular method. So you can do this. Remember, a tabular method works really good if you have like a polynomial and any one of these things, like an exponential, which is what we have here, a sine function, or a cosine function. It works really, really efficiently at that particular setup. So game on, we have the first version. We have a polynomial x squared times an exponential e to the negative x. So I'm going to set up the integration by parts by setting up the u and the dv. And the u is always the polynomial part because you're going to keep taking the derivative until you get to 0. You need that stopping ground for the tabular method. Now I'm going to do some work on the side over here because I want to remind myself that, like, yes, well, let me switch back here. dv is e to the negative x, but I actually want to take that and work on it. You're integrating e to the negative x dx. So that's what v is. So remember, you're integrating. Technically, you're doing a u substitution. It's not babyish to sit here off to the side and actually go through the motions of, like, what would my antiderivative be? Well, it would be negative e to the u. It would be negative e to the negative x. So it feels like it's a derivative. It's not. It's an integral. You have this extra negative flying around when you integrate e to the negative x. So I'm going to go straight down this line using that rule. Now again, if I do it again, the integral of e to the negative x is negative e to the negative x, and those double negatives cancel out. And then here it comes back again. Now remember, the third component of your integration by parts is start positive and alternate those signs as you go through. Also, remember with integration by parts, your antiderivatives, the parts of your antiderivative are u times v. You don't want to go straight across because remember, this is dv. So u times v, here's another u times v, and here's another u times v. Okay. So I'm going to write down my antiderivative, and let's see, I have x squared times negative e to the negative x. So that would be negative x squared e to the negative x. I think I'm going to give myself some room before I write that. Give myself some room. Negative x squared e to the negative x. My next one is negative 2x e to the negative x. And my third part is negative 2 e to the negative x. Now, that is your antiderivative. Keep in mind, you know, running in the background here, that you have this limit as b goes to infinity. That's there. That's a tag along. But now your process becomes, okay, I've handled the antiderivative. I got over the integration by parts. Now I'm really just executing the fundamental theorem of calculus. I am going to replace a b wherever the x was and just go for it, right? Of course, I still have this limit flying through my problem. I'm going to handle that last. So you start with it and you end with it, right? So I'm going to now put b's in wherever the x is. So negative b squared e to the negative b. Negative 2b e to the negative b. Negative 2 e to the negative b. And now let's throw the zeros in. You'd end up with, well, 0 times e to the 0, that's 0. Negative 2 times 0, e to the 0, that's 0. And then here, negative 2 e to the negative 0, which is just e to the 0. So let's put all this together. I have negative b squared e to the negative b. Negative 2b e to the negative b. Negative 2 e to the negative b. And let's be careful. I know I have these zeros, but this last guy is not 0. Negative 2 times 1. So minus negative 2 is plus 2. Now I have to figure out how to evaluate this limit, because once you've executed the fundamental theorem of calculus in its entirety, your position changes to pivoting to, I need to evaluate this limit. And let's be clear about what's happening here. E to the negative b, what does that graph look like? I tend to be very graphy when I think things through. This is what e to the negative x looks like. So if I let b go to infinity, let's just pay attention of what I have here. I have negative infinity squared, which would be, well, negative infinity. And I have e to the negative infinity. So what does that mean? That means as I kind of move towards infinity on this y equals e to the negative x graph, I end up with 0. This is a serious problem for me. That is an indeterminate form, if you remember, from way back when in Unit 1. That is an indeterminate form. Luckily for us, we have a very efficient way of handling this because I can use L'Hopital's rule. Well, I should be able to. But the only way I can use L'Hopital's rule is if I take this thing and make it look like fraction. Lucky for me, we can very craftily move this e to the negative b down into the denominator. Actually, I'm going to do that across the board because that's a legal thing to do. You know, I'm now in limit mode of like, what am I going to do with this? How do I evaluate it? You could legally just say, let me just throw that negative exponent down there in the denominator. That gets rid of the negative part, right? Same thing here, negative 2b over e to the b, negative 2 over e to the b, and then you're plus 2. So when I go through it at working this out, I have a little bit of an issue with what's going on. If b goes to infinity, well, I have another indeterminate form, let's say, right? Because I have negative infinity over infinity. Because remember, here's the graph of e to the x. That goes to infinity. That's another indeterminate form, but a manageable one because now you can actually execute L'Hopital's rule. I can use that rule to really get myself going. Now, if b is going to infinity, what I happen to notice here is you have 2 over something going to infinity, and 2 over something going to infinity. That whole thing falls off and it's just 0. So I have these two issues going on about like what is happening with this statement and how do I address it. So you can definitely use your skills from Unit 1. Let's use L'Hopital's rule. And then that's a 0, so I'm just going to skip ahead and do the plus 2. Now again, I kind of see the same issue happening here, right? If b, I should say b, if b is going to infinity, well, this term is going to 0 again. And you can continue to use that L'Hopital's rule. Totally great. Negative 2 over e to the b, that's a 0, so just plus 2. So now I have the same issue. You have this kind of, that term, it just keeps going to 0. So what do I end up having? Well, I evaluated this limit, and I have 0, something tending towards 0, plus 2. That's 2. So this was a meaty one for sure. I mean, it was obvious in that your limit of integration was infinity, but boy, you have to use integration by parts to get this to nail down, and you actually have a real number at the punchline here. So what am I going to say? I'm going to say this integral converges to 2. So while it's an infinite region, right, you're talking about the area under the curve x squared e to the negative x, from 0 to infinity, it has a finite value that it's approaching. That area is getting closer and closer to 2. Okay, we don't want to say equals 2 necessarily, it's just headed towards 2. So interesting that an infinite region has a finite area. Okay, so so that was definitely more involved. And here's where you see like all the nuts and bolts of this course start coming together, right? I'm pulling from Unit 1, I'm pulling from Unit 3, I'm also pulling from Unit 2. We've got a lot of execution of integration here. Here is our last example, which is very similar to another one that we had done, namely example 5. This is the same kind of issue where, not necessarily, but I definitely see that I have 2 problems, and that's an issue. I see my limits of integration are negative infinity to infinity. That is doubly improper. You can't handle this in one shot. So when I say it's like example 5, what I mean is the only way to address this integral, this improper integral, which stands out, is you have to create 2 integrals out of this one. You have to. So I'm going to do that. I'm going to say, okay, well, let me just pick this apart. Let me go from negative infinity to some value. I'm going to leave it open for right now. And let me add to that the integral from some value to infinity. And I mean, you can pick your favorite number in here. It does not matter what you choose. You just need some kind of real number to anchor it. Something fixed, something that you can use to move forward. I can't have both limits of integration be limits on the outside. I can only handle one problem at a time. So you could break it up around 0 or 1. Those are the traditional things. You could use 7 if you really felt like it. I'm going to use 0 because that usually works in a lot of situations. If 0 isn't good, then choose 1. All right. So now you have not technically addressed the improperness yet, but you're well on your way. You've shown that this has to be broken up, which is a big deal. What I now have to do is address each one of these problems, right? I'm going to address that lower limit of integration and say, okay, let's do that. Let's say the limit as a goes to negative infinity, and let's put that integral from a to 0. Okay. Now I'm going to add to that. I have to address my other problem. My next integral has its problem area here at infinity. So I'm going to have to address that problem by letting the upper limit of integration of that integral go to infinity. Okay. So I can say here that you have addressed the improperness. This is worth a lot to me in terms of points on the Unit 3 test. But now you have to sort of pivot, change gears. You've addressed the improperness. Now you have to be all in on how do I evaluate that integral? What is the antiderivative of 1 over x squared plus 9? Lucky for you, you remember how to do this from Unit 1. Because this is an arctan looking derivative. I'm just going to morph it perfectly to suit my needs. If I let u equal x, which I still have a follow through, that du is dx, and I let a equals 3, what I end up with this integral is 1 over u squared plus a squared du. So that antiderivative is 1 over a arctan of u over a. I'm going to switch back to like my x variable, because you were working so hard on what that antiderivative is. I have to now pay attention. Well, wait a minute. I'm supposed to be plugging this in from a to 0. And don't forget, at the end of the day, this is really going to turn into a limit question. You're just still working on that fundamental theorem of calculus. You're still sort of dealing with evaluating it. So let's do it. Let's plug in 0. Let me switch my color back. 1/3 arctan. If I put in a 0, that's just 0. Minus 1/3 arctan of A over 3. All right, we're really getting into something here. Okay. Now, we have to be able to evaluate inverse trig functions. The arctan of 0 is in fact 0, so 1/3 times 0 is just 0. 1/3 times 0 is just 0. Now here's what's interesting. All right. Arctan is tending towards negative infinity. I know if you kind of just like substitute the negative infinity there, negative infinity divided by 3 is still negative infinity. So I'm going to kind of see it like this. You have something like this that's tending toward negative infinity. The inside is going to negative infinity. Okay, so let's think about what that is going to do. Wildly enough, there's a fixed number for this. I'm like a magician pulling this out of my hat. We once upon a time talked about the graph of arctan. The arctan graph does have domain from negative infinity to positive infinity. The arcsine and the arccosine did not. They were fixed and closed graphs. Here is your image of the arctan graph, just so that you can see it. It looked like this. And it had these creepy horizontal asymptotes, and they were different on the left-hand side and the right-hand side, right? As you approach infinity, you're tending toward this y value, which happens to be pi over 2. And if you tend towards negative infinity, you're approaching this horizontal asymptote of negative pi over 2. So what I'm saying is, well, right now we have the arctan, and the inside is tending toward negative infinity. That means I'm approaching that output of negative pi over 2. Okay, let's throw that in. Negative 1/3 times negative pi over 2. That's what I'm doing. This is what's happening here. So my answer to this, evaluating this limit, is pi over 6. Okay. That's a lot, right? Now, that's only 1/2 of my answer. Now, the last time I broke something up, my first integral diverged. I didn't have to worry about the second one. Well, now I do. I got a number here, so now I actually care about going back to this other guy, this thing right here, and say, well, now I got to figure that out, right? Well, luckily for you, all of your hard work on the antiderivative has already been exposed. It's the same exact function, right? So you're at the same moment in a way. It's just the issue of carrying on from here. So what does that mean? Let me try to get this in a spot where I have room. I'm gonna leave that limit, right? It's the limit as b goes to infinity. Now my antiderivative is going to be the same antiderivative that I had here. 1/3 arctan x over 3 evaluated from 0 to b. Now let's do it. Now remember, eventually this is going to turn into a limit problem. What do I have? I'm replacing anywhere there's an x with a b. And anywhere there is an x, I'm replacing it with a 0. Trying to squeak that in there. Now again, b is going to infinity. So what I end up having here, let's just think about it in the back of our minds, what's going on. You have 1/3 times the arctan of something tending towards infinity. Think about your graph. If you look at the graph of arctan as x goes to infinity, it's pi over 2. That's your limiting value. That's what is your output doing? What are your y values doing, right? When we talked about limits. And so then I can answer this. It's 1/3 times pi over 2. Now, evaluating this, right? Arctan of 0 is in fact 0. So it turns out that this is also pi over 6. Now, how do you answer this question? as a whole question, right? Because what we were charged with figuring out is we were charged with figuring out the whole entire thing, soup to nuts, from negative infinity to positive infinity. We have these two pieces. This integral turns out to be pi over 6, and this integral turns out to be pi over 6. So all of this boils down to this integral that we were charged with finding, keep on going, right? Here's all my work. Turns out that it equals pi over 6 plus pi over 6, which is 2 pi over 6, which is pi over 3. So what are you going to say? You're going to say the integral converges to pi over 3. That's pretty wild. Now again, it is an infinite region with a finite value to the area underneath this function. That's a pretty loaded statement there and probably is messing with your head. This is a very important tool, this idea of improper integrals and going to infinity on an integral. This is a very important feature both for Unit 3 and Unit 4. We will definitely come back to this idea in the process of sequences and series, which makes up the last component of this course, which is Unit 4.